press the record button. All right, so I kind of feel like I lost you guys a little bit on Tuesday, so I wanted to take one more shot at explaining those two component diagrams. I let him be in the camera if you want.
That's fine.
So we showed you with the pressure composition diagrams kind of a derivation that showed that we could express the pressure as a function of the mole fraction of the components in the liquid phase or the mole fraction of the components in the gas phase. And that was just kind of to demonstrate that it was possible to mathematically show what the total pressure of the solution was based on either one of those variables. From there, we went to this graph where we looked at, we said that now we're going to hold pressure constant, we're going to let temperature vary, and so we have the pressure of the vapor as a function of the mole fraction and temperature on that other graph. So this is the graph that is most useful when we look at things like fractional distillation. Basically, these two lines represent the same exact reality, essentially the same physical point in space of that solution. The line down here, if you move along the x-axis in the mole fraction, you move up to that line tells you what temperature you'll have equilibrium between the solution and the gas phase. If you move up or down from that temperature, favor one state or the other, the liquid phase or the gas phase. And the point on that line that you intersect gives the mole fraction of the components in the solution. This line right up here communicates the same thing. It tells you what what temperatures and mole fractions will be in equilibrium, except now this line, the points on this line represent the mole fraction of a component in the gas phase. To look at the same point in space, you essentially draw a vertical line at a constant temperature. So you pick a constant temperature, and sorry, not vertical, horizontal line. You draw a horizontal line across this graph, and the place that it intersects the two graphs, those 2 points will represent the same exact temperature, right? And so whatever mole fraction we intersect here for the liquid phase, you'll have this mole fraction over here existing in the vapor phase above. Right? Go ahead.
Do the fractions always equal 1?
Yeah,
Do the what?
Fractions always
fractions.
equal 1.
The fractions
the
always
mole
equal?
fractions, they always add up to 1.
The mole fraction in the liquid and the vapor?
Yeah. Like when you add them together,
I don't believe so.
No?
No. I don't think so. It's not quite the way the math works on that. When you have a heavy mole fraction, or when you have a total mole fraction here that is, an x component or y component that's much, that's approaching 1, the mole fraction of that component in the liquid and the vapor will end up being both greater than 1, and so not greater than 1, but they'll be greater than half. So those two added together will be greater than 1. Anyway, enough said with that. What I wanted to do is to go back to a more physical picture of what's happening. So we said that a graph like this holds when we have a situation where AA, B, and AB interactions are equivalent. And that's not entirely true. There's never such thing as AA, AB interactions being equivalent, but for these ideal solutions, we're going to pretend that they're roughly equivalent. In that case, what happens is this. I'm drawing right now a top view of a cylinder, of a flask we're looking down on. And this flask is filled with A molecules, B molecules, case that these interactions are roughly equivalent, it doesn't matter what molecules what other molecules a particular molecule is surrounded by. That molecule has its own characteristic tendency to leave the liquid phase and go into the vapor phase, regardless of what interactions it's feeling from the molecules around it, right? If AA and BB interactions are equivalent, then this little B molecule here doesn't care if it's surrounded by A molecules or B molecules or half A or half B molecules. It still feels the same kinds of magnitudes of pull, kind of pulling it down into the solution. In that case, if all the forces are equivalent, we can kind of say that whichever species, A or B, has the largest vapor pressure in general, that will be the species that has the greatest tendency to leave the liquid phase and go into the vapor phase, right? And so we have this characteristic that if I've drawn here the mole fraction of some component going towards 1. You see that that component has a mole fraction of 1, the boiling point temperature is the lowest. That means that component is the most volatile component. And you see that relative to the liquid phase, the vapor phase is always enriched in that component. That means that more of that component is leaving the liquid and going into the vapor than the other component. Go ahead.
Does that have to do with chemical potential?
It does have to do with chemical potential. We're not going to use any math right now to try to argue this. We're just going to kind of do it qualitatively. But yeah, ultimately everything has to do with chemical potential. So when we've got that situation where the AA interactions, BB interactions, AB interactions are all roughly the same, then what ends up being the dominant factor is which of these guys has the highest vapor pressure, which one is the most volatile. And if on this graph I'm drawing the mole fraction of the most volatile component, which you can tell because when we get to mole fraction is equal to 1, the temperature is the lowest, then the vapor will always be enriched. The vapor will always have a larger mole fraction of that component than the liquid, right? So Y is the mole fraction of the vapor, X is the mole fraction of the liquid. And we look, and at any particular temperature, Y is larger than X. So we're saying that that species, the most volatile species, is leaving the liquid state and it's going up into the gas state, right? So that is the general pattern. But there are exceptions, where not everything behaves that way. Not all A, B, interactions are equivalent. And we have two cases. Sorry, I gotta figure out where these are drawn. It's not being on that one. We have two different cases that can potentially be occurring. And those cases are that the interactions between an A and a B molecule are stronger than the interaction between an A molecule and an A molecule, or a B molecule and a B molecule. And in that case, when an A molecule is adjacent to B molecules, it's pulled into the liquid phase with more force. And so it's harder for that molecule to be kicked out of the liquid phase and into the gas phase. So let's redraw this here. And let's say that we have a situation where we just have a few B molecules. We've got a bunch of A molecules. So A is in excess and B is a minor component. In that case, this B molecule here and all of the A molecules around it, I'm going to just draw a circle here around this whole unit. Because A-B interactions are stronger than AA interactions or BB interactions, this whole unit here is tied to the liquid phase with more force than, say, these two A molecules that are, or these three A molecules that are all kind of sitting together, right? See, these A molecules have the benefit of being bound tightly to this B, and that B has the benefit of being bound tightly to those A molecules. But these A's that are surrounded with other A molecules, they aren't bound as tightly because AA interactions are weaker. So you start raising the temperature on this thing, and what's going to happen?
A gonna vaporize.
This unit's going to stay behind, and these A's are going to tend to pop off. Now, it's not true that all of these units will stay behind. Some fraction of them will leave, but a good number of them will stay behind with the solution. And the A molecules will go off into the gas phase. Go ahead.
What did you say the unit's going to stay behind again?
Say one more
Why
time.
did you say that unit's going to stay behind again?
Because we're saying that A-B interactions are stronger. The potential, the electrostatic, forces tying A and B molecules together are stronger. Go ahead.
And then the AB unit that you were talking about, once like it theoretically is eventually driven into the gas phase, the A's and B's will like break apart, right? It won't sort of stay that little compact. Like,
Yeah. I mean, anything in the gas phase, they separate the gas phase molecules. Go ahead.
Is this kind of like the same idea when we were talking about how you can't purify anything?
Yeah, this is exactly what we're getting at. This is exactly what we're getting at. Okay, so imagining that these interactions are stronger, then for the most part, when you distill this and you pump stuff off into the gas phase, you're going to be pumping A molecules off into the gas phase. And these A molecules that are surrounded by the B molecules will stay in the liquid phase, right? And there'll be some ratio of A's to B's that is the strongest and most tightly packed unit, and that unit will tend to stay behind. So what happens is that if we look at this guy, we're talking about point B here, and we're referring to A molecules on this mole fraction line. So we're at point B where these A molecules are in excess. You boil this thing, you go up to here, the gas phase is going to be dominated by A molecules. And as those A molecules leave the gas phase, what's left over in the liquid has a lower ratio, we're moving back to the left now, it has a lower ratio of A to B molecules. And that's because these guys are pumping off, and this unit is remaining behind. And so if you distill that solution, your liquid phase, your vapor phase is going to go towards pure. Mole fraction of that thing moves to 1 after repeated distillations. The liquid phase that's remaining moves backwards in concentration until eventually it reaches the point where you have all units like this, all of these favorable units, whatever particular ratio has the strongest interactions, the whole thing that's left behind has units like that in it. And that's a maximum boiling azeotrope. Once you get to that situation, when you start distilling, only these units pop off. And so your vapor phase and your liquid phase stay at constant composition, right? And that's what we're trying to show with this graph, is that the liquid remaining moves backwards towards the maximum boiling azeotrope, and the gas phase popped off moves towards being pure. And after repeated distillation steps, you get in the liquid behind your max boiling azeotrope, and in the gas phase you get something that can be made relatively pure. So that situation is the kind of, well, not this one here, but the one we just discussed, is the kind that nitric acid and water obey. The opposite effect that we can observe, where we have what's called a minimum boiling azeotrope, is when these units are the least well bound. So A molecules next to B molecules and B molecules next to A molecules have the weakest forces. And so they have the weakest forces holding them to the solution. These A molecules surrounded by other A molecules have the strongest forces tying them down to that solution. So what happens then is you boil this thing, and units like this pop off into the gas phase, leaving behind whatever component was in excess. And so now, whatever is remaining in your flask moves towards being pure, and the other one, or gas, moves towards being pure. Now, whatever was remaining, the A, only A molecules, those stay behind because they're experiencing the strongest forces. So what's left in the liquid moves towards being a pure solution. But now the gas phase is filled with those units that have the maximum attractive forces. And so you see here, we've got our vapor line here and our liquid line here. In this case, the liquid moves towards being pure, and the vapor moves towards the left on the curve, towards the minimum boiling azeotrope. And eventually the vapor reaches a composition where it's uniform at whatever the most favorable ratio is to have that, the minimization of those interactions. Okay? All right, so I think that's about all I wanted to say about that. You guys have to pardon me, I'm really tired right now, so I'm going to sit. We're going to switch gears now, and we're going to start talking about the Gibbs free energy and chemical potential and requirements, or kind of the state of what is equilibrium. And so just as a reminder, when we derived the Gibbs free energy, we said that we had the requirement, we're going to define that anything that happens spontaneously was going to result in an increase in the entropy of the system and the surroundings, right? And so we threw up an equation that said delta S of the system plus delta S of the universe, or sorry, that should have said surroundings as the universe. Delta S of the system plus delta S of the surroundings is greater than 0. So anything that happens spontaneously, the sum of the delta S's is going to be positive. And then we said that delta S of the system, we want to phrase this in terms of just variables that relate, or state equations that relate to the system. Delta S of the system can be left, but delta S of the surroundings we can express as negative delta H of the system over T. Because delta S is Q over T, and for a constant pressure process, the Q is delta H. And whatever Q is fed into or leaves out from the system goes into the surroundings. So we throw a negative sign in front of delta H of the system, and that gives us the Q that goes in the surroundings. So if we want to express delta S of the surroundings, we can call it negative delta H over T, right? Throw that in there, we do some math, we multiply through by T, and then we move it to the other side, and we get this equation that says that for spontaneity, this equation delta H of the system minus T delta S of the system has to be less than 0. And then we call that delta G. We call that we define Gibbs free energy as H minus Ts, right? And so delta G is delta H minus Ts. That's our equation that tells us whether or not something's going to be spontaneous. The T is the temperature of the system and the surroundings. We're going to define this as being a constant temperature process. And so we're saying that if the system and the surroundings are at the same temperature, then we just write one T up there. We call that T. And it's a constant pressure process because we want delta H to be equal to the Q. So delta H is Q of a constant pressure process. So this Gibbs free energy equation applies at constant temperature, constant pressure. We have other equations that govern spontaneity when you have conditions that aren't constant temperature and constant pressure. But constant temperature and constant pressure are the most common conditions, and so delta G is the most useful equation for discussing spontaneity. We define mu, the chemical potential. Mu is just another way of saying delta, or G, Gibbs free energy, except it's defined as the Gibbs free energy per mole. So G in general is the Gibbs free energy. When you look at mu, you know that they're talking about how much free energy is associated with a single mole of a substance. We went back to the total differential of the Gibbs free energy. We did a big long piece of math and we said that dG was VdP minus SdT. And the reason we did that is because we wanted to have an expression for how the Gibbs free energy varied from non-standard conditions. At constant temperature, that SdT term goes away, and we have that dG is VdP, and we went right into an ideal gas, and we said, okay, well, in that case, if Gibbs free energy changes as VdP, then we can say that at constant temperature, the G of any pressure is equal to G naught plus the integral of VdP from the initial pressure up to the final pressure. Okay? And then we threw in the volume expression for an ideal gas, nRT over P. And we took the integral of that from the initial to the final pressure, and we came up with this expression. We said that G is equal to G naught plus nRT line P final over P initial. Right? And that's the way that the Gibbs free energy varies with pressure. And so if we know G naught for an ideal gas species at 1 atmosphere, we're going to define P naught as 1 atmosphere, then we just take the ratio, the natural log of the final pressure to the initial pressure, and that gives us the change by which G varies with pressure. Divide this whole thing by n, there should be an n right there, and we've turned it now into the Gibbs free energy per mole. So now we're using the notation mu. And the chemical potential then, Gibbs free energy is mu naught plus RT natural log of P final over P initial. Again, assuming that the initial pressure is 1 atmosphere, then that guy ought to be mu is equal to mu naught plus RT over P. Right? This was useful. It's useful if we're talking about gas-phase species, but we're not always dealing with gas-phase species. Oftentimes we're dealing with solutions. And so we wanted an expression that told us about the Gibbs free energy of a species in solution. And for that, we used Raoult's law. And we said that for solutions that obey Raoult's law, we know that the pressure is proportional to the mole fraction. And so we said that we can take this mu is equal to, mu of the solution is mu to the vapor. When you have vapor in equilibrium with a solution above it, the chemical potentials of the two species are equal. So we said that we can take that point of equilibrium and we can write an equation based on it. Mu solution is equal to mu of the vapor. Is mu naught plus RT line P. That's the mu of the vapor we just derived. But now the P above the solution is the mole fraction times the P of the pure solution if that solution is obeying Raoult's law. This part can be broken apart into two pieces. This RT line P of the pure can be joined with the mu, and we get a new mu star. And we say that mu of the solution is mu star plus RT times the natural log of the mole fraction. And so now we have an equation that tells us what the chemical potential is of a species in solution. Right? And it's proportional to the mole fraction. It turns out that the mole fraction for a dilute solution is proportional to the concentration. And so we can also write that mu of a species in solution is equal to mu star plus RT times the natural log of its molar concentration. We'll end up seeing delta G's or mu's based on concentration as we move on. Go ahead.
What's the difference between mu naught, and mu star?
Mu star is the one that refers to the solution and it includes mu naught of the gas plus RT natural log of the pressure of the pure solution. This takes a while to wrap your head around. I encourage you right now to just kind of accept it and go back and ask yourself in the next 3 years what the hell it means. That's what I did. Okay, so we've got the chemical potential of the solution as a function of the mole fraction or the concentration. And that ends up giving us ways to relate the Gibbs free energy of gas phase species and solution phase species. I wrote everything that I wanted to say just so that you guys have them on notes and you can go back and read it later on your own. But I'll just kind of speak in general right now. Not every gas behaves like an ideal gas, and not every solution behaves as an ideal solution. And so these two equations that we have, mu is mu naught plus RT line P, and mu is mu star plus RT line XA, those only work for species obeying ideal gas law and ideal solution laws. And so we need to have an equation that will allow us to relate species that don't obey those. And for those, we replace P or XA with something called the activity. And the activity, if you're talking about a gas phase species, essentially is just some multiplier times the pressure of the ideal that accounts for what the actual pressure of the species is. If the pressure of the species isn't what you would expect from an ideal gas, then you observe what that pressure is, and you throw in a multiplier that accounts for that. And so your activity ends up being that multiplier times the pressure of the ideal species. You could do a similar thing for species in solution. But basically that gets us to the point where we can write that mu, chemical potential now, is mu naught plus RT times the natural log of the activity, where the activity is whatever it needs to be to fit the physical reality of the situation that we're in. Right? Whatever physical realities that thing is obeying.
Can it be less than or greater than 1?
Yeah, it can be less than or greater than 1, depending on if you're talking about a gas phase species, depending on whether or not the pressure of the species is greater or less than 1. The activity can be greater or less than 1. So the activity, they observe a particular species, and they say, okay, well, it actually varies this way, and so they put a coefficient in there that fits its observed behavior, right? So this is the equation that we're going to be working from. The chemical potential is whatever mu naught is plus RT line A. If we're talking about an ideal gas, that's mu naught. If we're talking about a solution, that's mu star. If we're talking about a gas, it's mu naught. If we're talking about a solution, it's mu star. So we'll move from there to here briefly. We saw that for the solution species and the gas phase species, that the chemical potential increased with concentration. So we had RT natural log of pressure for the gas species, we had RT natural log of the mole fraction for the solution phase species, and needless to say, pressure increases with the amount, mole fraction increases with the amount, and so the chemical potential of any species increases with the amount of species.